All right. So in the last class, I just introduced you to the subject and recall that the main goal is essentially to derive bounds on the following quantity. What is the probability that some function of n random variables deviates from its expectation by a certain amount? All right. And as we saw in a couple of examples, if we are able to derive tight bounds on this particular probability, then it allows us to analyze various problems such as communications in machine learning, data compression, so on and so forth. And we'll see a bunch of different examples as to where this can be used. Okay, but the agenda for maybe the first half of today is essentially to cover the basics of probability so that we are set and we can continue with the main topic itself. Right. So recall that in the last class I defined the probability space. So the sample space is just the collection of outcomes, and this can be finite or countably infinite or uncountably infinite. All right, and out of the sample space, we're not interested in all possible subsets of these. We take a special subset of or special collection of subsets of the sample space, which we call the event space. And we look at the event space for various reasons. So firstly, the event space is kind of structured. It's not any arbitrary collection of subsets. It has to form a sigma algebra, which means that it has to satisfy these properties. And the reason why it has to satisfy these properties is because it allows us to define a measure or define a probability measure on these events. In the sense that if we define a measure or a probability measure on some basic events or basic sets, then we can also derive the probability measure for more complicated events or complicated subsets. Right? And in some sense, the event space is the collection of all events or collection of all sets for which the probability is well defined. If there is some event or some subset which is not in this event space, then we can't really say anything about the probability of this. All right. And recall that a probability measure is essentially defined in the following way. It's some measure on, so for every event you assign a non-negative real number, a number between 0 and 1, such that the entire sample space has measure 1. So the probability that something occurs is 1. And if you have disjoint events, then the probability that at least one of those events occurs is essentially equal to the sum of the probabilities of each of those events occurring. Right? That is what this is saying. Now, in the previous class, we also had a little bit of a discussion as to why you can't choose the event space to be the entire power set. And perhaps one way of looking at this, although it's not a rigorous proof, but one way of thinking about why you can't choose the entire power set as your event space is the following. Now, suppose that your sample space is the real line. All right, let's fix that for now. And suppose that, well, we want to define a probability measure on this. So maybe we start off by defining the probabilities of intervals. Right? So for every interval of the form a comma b, I assign a probability. I know what the probability of each interval is. Now, if I have a more complicated subset, which is maybe, so I can always write, perhaps I can write this as a union of disjoint intervals. Then if it is a union of at most countably many disjoint intervals, then I know that the probabilities is the sum of the probabilities. If it could also, I could construct complicated events where the event is a union of countably many disjoint intervals. Right? In which case, again, the probability of this particular event is a series. So it is summation I equal to 1 to infinity of some p of ai, where all of the ai's are disjoint. Now, as it turns out, because it's the entire real line, the sample space is the entire real line, you can come up with very weird and complicated events or subsets which you can't express as a countable union of disjoint intervals. So for example, I could construct something very weird which is an uncountable union of disjoint intervals, right? Again, it's not easy to come up with such constructions, but believe me, you can sort of intuitively get that it is possible to construct sets which can be expressed as an uncountable union of disjoint intervals, right? You can think of sort of, you can shred the entire real line into small pieces, maybe vanishingly small pieces, and you can come up with very weird sets. But now, how do you define the probability for this really complicated set? It's no longer, you can't express it as a sum of probabilities because it's an uncountable union, right? And and it is possible to construct such events or construct such sets wherein if you try to compute the probability of this event in two different ways, then you'll get two different answers. So in other words, for such complicated events, it is not possible to define a consistent probability measure. So that is why we always take the event space to be, for example, the event space which is generated by all possible countable unions of disjoint intervals. So you take intervals and think of all possible events that can be expressed as a union, a countable union of intervals. And that is the class of events that we are going to be interested in. All right. So you have some basic events, for example, intervals, for which we can define the probability. All right. We define the probability for all intervals, for example. And the only events for which we have well-defined probabilities are those which can be expressed as a countable union of intervals. Right? And such a sigma algebra is called the Borel sigma algebra, if you've seen it before. Right. So one sort of event space or sigma algebra that you always encounter in probability is the so-called Borel sigma algebra, which is the collection of all subsets of R, or in general R to the n, which can be expressed as a countable union of disjoint intervals. Right, intervals of the form, let's say a comma b.
Sets countable union of disjoint subsets. The six.
Sorry, countable union of
Disjoint subsets.
yes.
It's the same, right?
As same as
Interval unit.
no. So for me, an interval is always of the form a2. It's a continuous interval, right?
Okay. Discrete set of elements. Suppose I have
No, it's a
countable
continuous.
union of power set cannot always be a event space, right?
Correct.
Out of the power set, I'm taking all possible countable unions of disjoint
Intervals.
subset, right?
All subsets that can be expressed as a countable union of disjoint intervals. The number of sets in the Borel sigma algebra is going to be uncountable. Right? The size of the Borel sigma algebra is uncountably infinite. But every set, so remember, the Borel sigma algebra is a collection of sets. All right? Every set in this Borel sigma algebra, it is either an interval or it's a union of intervals. But union of how many intervals? A union of countably many intervals.
There's an infinite number of elements, but countable number of elements basically within the set.
No. So again, there are two things to distinguish between, right? So what does a sigma algebra or what does an event space look like? It's a collection of sets. It's a collection of event, right? So the Borel sigma algebra, for example, can contain 1, 2 is an element of this Borel sigma algebra. Even a set of this particular form, union I equal to 1 to infinity, maybe 2 to the I plus 1. Okay, this is a set, and this set is a union of, it's a countable union of intervals, right? Specifically intervals. All right. So this belongs to the Borel sigma algebra. This belongs to the Borel sigma algebra. All right. In fact, most sets that you can think of all belong to the Borel sigma algebra. It's very difficult to come up with an example of a set which does not belong to the Borel sigma algebra. All right. Yes.
If the set is like the probability, the sample space itself is discrete.
If the correct, if the probabilities, if it's discrete.
The same be valid. Like let's take the case of rolling a die.
Correct.
How do you?
So in that case, you can always choose the event space to be the power set. In fact, that is what we will always do. If the sample space is finite, then we're always, in fact, even if it is countably infinite, we're always going to choose the sample space, the event space to be the power set. Yes.
The Borel sigma algebra will be the power set of the.
Sure. Again, it depends on how you define the Borel sigma algebra.
Okay, if you define on Borel sigma algebra,
if you consider, okay, I guess what you're trying to say is, if you suppose that the sample space is a countable subset of R, right, then the power set will be a subset of the Borel sigma algebra.
But if the sample, the underlying space is not R, some sample space.
Okay.
Then we consider the Borel sigma algebra of that sample space. Will it be equal to 4?
How do you define the Borel sigma algebra of an arbitrary set?
If we are considering there is an underlying probability space, right? Sigma, F and.
Correct. So what is your F?
If I am considering F as a Borel sigma algebra of.
How do you define the Borel sigma algebra of an arbitrary set?
Okay, it is a smallest sigma algebra generated by this.
Generated by?
A sigma algebra generated by sample space.
What does that mean?
Smallest sigma algebra.
So typically the Borel sigma algebra is defined in terms of either intervals or some sort of a basic set, right? And this happens to be the smallest sigma algebra that is generated by intervals, right? So you need an underlying some kind of a topological space to define the Borel sigma algebra. You could define some way, but one way of thinking about it is, yeah, so always if omega is finite or countable, then we always take f to be the power set. Right? If it is uncountable, for example, if it is either the reals or some uncountable subset of the reals, then we take the underlying event space to be either the Borel sigma algebra or something a bit larger, which is called the Lebesgue sigma algebra.
Sigma algebra is necessarily belong on R.
Not necessarily, but some kind of an uncountable space or some kind of a space which has an underlying topology that is defined.
So all event spaces will be a subset of taking set, right?
I'm sorry?
All event spaces, possible event spaces of a particular sample space.
All possible event spaces are
Whatever, we can choose a set of event spaces, right?
correct.
I mean, I can just take one set of interval and just tell that is my event. Or take a,
Fine, yes.
it will always belong to, will be a subset.
Not necessary. I could construct more complicated event spaces which are bigger than the Borel sigma algebra. In fact, that's what I'm getting to. So the Lebesgue sigma algebra is something that includes the Borel sigma algebra and something more. All right. Right. So the Lebesgue sigma algebra is something that contains the Borel sigma algebra, and again, these are technical details. These are not something that I'm going to get into, but you should at least know what these terms are. Right? Because if you read any book, for example, on probability, you'll encounter these terms over and over again. If you want to understand it in full generality, you have to take a course on either real analysis or measure theory. But again, that's not the point of this particular course. If you're interested, then it's a nice thing to pick up a book on measure theory. But it's at least good to be familiar with the terms and know what they intuitively understand what they mean. Right? So the Lebesgue sigma algebra is one way to think about the Lebesgue sigma algebra. It is the Borel sigma algebra. Along with some collection of sets, essentially all possible that have measure 0. Or in other words, when I say measure length 0. So for instance, if I take the set of all possible rational numbers, right? Is this set countable or uncountable? How many say it's uncountable? The set of all rational numbers, is it countable? How many say it's uncountable? It's actually countable because you can identify it with all possible pairs of integers, for instance, right? Because every rational number can be written as a by b, where a and b are integers. The set of all integers and set of all pairs of integers is countable. All right. So this, if you think about it, what is the measure of just one number? 0, right? If I just take a point on the real line, that just corresponds to one number, right? And this has measure 0. If I take countably many numbers or countably many points, what would be the measure of this set? It's 0. if I define the measure to be the length of that particular set, length as in the standard notion, the interval from A to B has length B minus A, right?
How that will,
I'm sorry,
how that will be
how that is?
zero.
So let me define the measure of an interval A comma B to be B minus A. If I consider just a point, a singleton set, what would be the measure of this particular set? 0, because you just take B equal to A and you get that, right? In fact, whether this is an open interval or a closed interval or a half closed interval, the measure is always defined to be by B minus A. And if you take a single point, then intuitively, I mean, so it's the natural notion of measure or length, right? So
But you said countably finite set or infinite set, if you take that measure also.
correct. So again, recall, if I have a set, so suppose I have, let's look at the set of all integers.
You define that measure to be the individual measure of the every.
So let's go step by step. So what is the measure of a singleton set? It's equal to 0, right? If I have two disjoint sets, what is the measure of the union of the two? So in fact, so if you take any countable set, countably infinite set, what would be the measure of that particular set? So it is just summation I in Q. Again, the emphasis here is that this set is countably infinite, and the measure of a union of countably infinitely many sets is equal to the sum. If it's a union of uncountably infinitely many sets, then this does not hold.
Is it because we don't know the individual elements?
That's because how it is defined, right? This is how we are defined. Yes. The interval from 0 to 1, it's an uncountably infinite set. Yeah. This is all of this is true. This summation is true only for countably infinitely many inputs. Right? That's exactly why if I try to do this for an uncountable set, then I would immediately come up with a contradiction, right? Because on the right hand side, if I had uncountably many events and each one had measure 0, then the sum would also have measure 0, right? But the length of the interval from 0 to 1 is 1. So this is equal to 0.
What can we comment about the measure of uncountable?
We can't say anything, just this is not enough, right? So for any uncountable set, you would have to essentially break it down as a union of disjoint intervals, and only then would you be able to find out the measure of that particular set.
The measure of countably finite.
The measure of any set which is a countable union of intervals, you can find that. Finitely many intervals, you mean?
Finite.
It's always equal to the sum.
So that will also be equal to
You mean the measure of any finite set? Correct. That's also equal to 0. And again, by measure, I mean this particular measure. So this is sometimes called the Lebesgue measure.
Sir, so all these It's because of how we define this measure.
This is exactly because there are some basic events or basic sets for which we have defined the measure. Right? So the measure of any other set is defined with respect to this and the properties of the measure. That's it. Is this okay? Any questions? All right, so let's.
But this collections of sets of measures 0, right, they won't belong to the Borel sigma.
There could be sets of measure 0 which don't belong to the Borel sigma. I mean, not all sets of measure 0 are outside the Borel sigma algebra. There are, of course, for example, the set of all rational numbers that belongs to the Borel sigma algebra. But there are more complicated sets which don't belong to the Borel sigma. Again, it's difficult to describe such a set, but you can show that there exist such sets.
So if I take randomly just points, in that sense,
they all belong to the Borel sigma algebra. It's pretty hard to come up with sets which are outside. It's hard to imagine sets which don't lie in the Borel sigma algebra. Right? Any set that you can think of, right, it will be in the Borel sigma algebra.
Telling that you can assign a probability to these condition of sets.
You can assign probabilities to anything in the Lebesgue sigma algebra. And in fact, for most, we will assume that whenever we're talking about, for example, random variables, which I'll come to, we will always assume that the underlying sigma algebra is the Lebesgue sigma algebra. Right? Because it's the Borel sigma algebra plus it gives us additional room. So whenever you define notions like the integral, all of that is defined with respect to the Lebesgue sigma algebra. No, set of all integers also belongs to the Borel sigma algebra. So I'm saying that there exist some sets of measure 0, which, as I said, it's very difficult to describe. Okay. Yeah.
And minus infinity to comma a close to interval is also an interval set.
That's an interval that belongs to the Borel sigma algebra. Yes.
How?
Open at minus infinity and closed on one side.
So can we able to express that one?
That is how it is defined as a Borel. So when I say, so typically,
Borel sigma is the collection of all the intervals minus infinity and everything can be expressed.
so one way of getting minus infinity to a is the following. So it's union 1 to infinity. For example, I comma a. I'm sorry, minus I comma a. So again, because I can construct countable unions, I can always get minus infinity to a. All right. So anyway, let's get back to probability. So as I said, you can construct depending on what kind of a random experiment that you're performing. For example, you could be tossing coins, you could be rolling die, you could be rolling infinitely many dice, tossing infinitely many coins, or something more complicated, right? So you don't want to keep worrying about what your sigma algebra is. Right? Ideally, you want some kind of a framework, a formal mathematical framework, that which says that, okay, I'm always going to choose this particular sigma algebra. Because for the reals, I define the Borel sigma algebra, the Lebesgue sigma algebra. If it's a finite set, then fine, I can just take the power set. But something more complicated, you don't want to get bogged down with all of those details. All right. So that's essentially why we have this concept of a random variable. So what is a random variable? A random variable is essentially a map. So you could be performing some arbitrary random experiment, and that could have outcomes. For example, if you're tossing a coin, the outcome is either a head or a tail, right? If you're trying to predict, let's say, the weather, then the weather could be, okay, you got so much rain and it was the temperature was so much, so on and so forth, right? What we want to do is essentially map all of these into real numbers. It's because we want a consistent framework, mathematical framework. Yes. All right. Because for every experiment, you don't want to again and again define what the sample space is, what the sigma algebra is, and then what the probability measure is. Instead, we will always assume a standard sample space, which is going to be the set of all real numbers, the standard sigma algebra, which is always going to be the Lebesgue sigma algebra. The probability measure, of course, it's defined by the CDF essentially. The sample space, whatever, it's some subset of that.
Because R and both same numbers.
They have the same size, so to speak, but we're always going to assume that 0 to 1 is in many cases restrictive. Right. So what is a random variable? It's essentially a map from whatever sample space you're dealing with to the set of all real numbers, but it's not any arbitrary map. What you want is, if you look at the set of all outcomes that get mapped to any interval, then this is a valid event. So it is any map from the sample space to the set of all real numbers such that every interval of the reals corresponds to a valid event. All right. Now, why is this particularly helpful? It's helpful because now if I know the probabilities of all intervals, then I know the probability of every event that I'm interested in. All right. So how do you define the probability measure for a random variable? I know, but in general, how do you, so if I give you a random variable, how would you specify the probability measure? How have you seen the probabilities? The CDF, right? Because, so these are going to be the base events for which you define the probabilities. Just one second. So this is simply the probability of x inverse of minus infinity to a. Yeah.
Is it necessary that it has to be minus infinity or any b's or something? A to b, like separate to b?
It doesn't matter actually.
Like any intermediate interval also should be belonging to the space. Like set a, b, or
I mean, if this happens, then any interval a to b is also, because you can write it as an intersection of two intervals of this particular form, right? Or what, set difference between two intervals. Because it's a sigma algebra, it's closed under unions, it's closed under countable unions, it's closed under countable intersections, it is closed under complements. So it is sufficient that this is an event. If this is always an event, then any interval of the form a to b is also a valid event. It's okay. So that's the power of using this particular framework. So once you specify the CDF, you specify the probabilities for all possible events. Right? And this is true irrespective of whether your sample space is finite or countably infinite or uncountably infinite. It's always true. The CDF completely specifies the probability measure. You don't have to worry about what the underlying sigma algebra is, what the underlying sample space is, nothing. Okay. Now there are different ways of so this the CDF completely specifies this, but for random variables, whether it's if it's continuous or discrete, there are more convenient ways of representing the probabilities. Right? For a discrete random variable, you can in fact specify the probabilities of all outcomes. That's a much easier way to specify the probabilities for a discrete random variable. So the probability mass function, which I will always denote Px. This is just the probability that x takes the value x. So I'm also, along with all of this, I'm also introducing to the notation that I will be using throughout this course. So capital letters will always denote random variables. Small letters will denote outcomes. And whenever I'm talking about the PMF, I'm typically going to use P subscript X. And the CDF will always be F subscript X. For a continuous random variable, if the probability density function exists, then that will be F subscript X. So if I have two different random variables X and Y, then I'm going to denote the corresponding PDFs as F subscript X, F subscript Y. All right. Okay, so let's just so that we are on the same page, let's take a very simple example. Suppose we are rolling a single die. Can you come up with a random variable for this experiment? Just the number that you see on top, right? So X could just correspond to right. So basically X takes the value 1 with probability 1 by 6, 2 with probability 1 by 6, 3 with probability 1 by 6, 6 with probability 1 by 6. All right. But I can define for the same experiment, I could define a different random variable. I could map it to 0, 1, 2, 3 up to 5. I could map it to anything I wanted, right? In fact, I could even map two events or two different outcomes to the same number. So I could map, so X could just take values 1, 2, or 3. So if the actual roll turned out to be 1 or 2, then it gets mapped to 1. If I get 2 or 3, then it gets mapped to 2 and so on, right? So for the same experiment, I can have different random variables. That's the point. Okay. So I won't go through all of these examples, but again, you can construct random variables for different kinds of experiments. Okay. So throughout this course, we'll be using a few probability distributions. It's good to familiarize yourself with those. I'm not going to introduce all of them here, so I'll leave it as a homework to go through them. So you should know what the probability mass function or probability density function, what is the mean, the variance, and the moment generating function is for all of these these common distributions, because we'll be using this over and over again in this particular course. All right. Okay, so again, quick recap. What is the expectation of a random variable? For a discrete random variable, you define it as summation over all possible outcomes, x times the probability that that outcome occurs. And for for continuous random variable with a PDF, it's just defined as integral from minus infinity to infinity, x times the PDF of x, right? And you can define the expectation of a function of the random variable as well. If g is a function then of x, then for a discrete random variable it is defined as summation over all x, g of x times PMF. And if it's a continuous random variable, then it's just the integral of g of x f of x. Okay, again standard stuff, nothing new. Now out of these expectations, there are some expectations that are special, and that is the moment, right? So the kth moment is just expectation of x to the power k, and we're interested in integers k equal to 1, 2, 3 and so on, positive integers. So expectation of x just gives you the mean, and expectation of x square is the second moment and so on. So I'll frequently use the kth moment and the kth central moment. So the kth central moment is just expectation of x minus the mean whole to the power k. When I take k equal to 2, I just get the variance. All right. And the moment generating function is just the expectation. It's a function of lambda. I'll denote this as p subscript x of lambda. This is just expectation of e to the power lambda x. Right? And why is it called the moment generating function?
The coefficients of x power k will be the k.
Okay, directly or something else?
Expectation.
Yes, but so what is e to the power lambda x? What is the Taylor series expansion? Yeah, so it's summation I equal to 0 to infinity. So what is it again? 1 plus, so
X power k by k.
so it's x power I, or if I want to call this k, then it is expectation. Okay, like this, expectation of x power k by k factorial, right? Or x power k lambda power k by k factorial. So this just turns out to be equal to summation k equal to 0 to infinity of lambda to the power k, expectation of x to the power k by k factorial. So this is called the moment generating function because you can obtain the kth moment directly from this. For example, if you take the derivative of this e to the power of phi x of lambda, if you take the kth derivative and set lambda equal to 0, then you directly get the kth moment. Okay, so hopefully you've seen all of this in your probability course. All right. Any questions so far? All right, good. So that sort of summarizes everything that the basics that we need in probability. So let's get to the meat of the subject. So as I said, the goal is to obtain bounds on the probability that a particular random variable deviates from its mean by a certain amount. So we're going to start with some very basic inequalities. Hopefully you've seen some of these inequalities already in your probability course, so some of them may be familiar. The first very basic bound is called Markov's inequality. and it's the following. So if x is a non-negative real number, it's a non-negative random variable, so it means that the probability that x is less than 0, this is equal to 0, and suppose that the expectation of x is equal to some quantity mu, which is finite, right? So if x is a non-negative random variable with finite mean, then for all delta greater than 0, we have that the probability that x is greater than delta, or greater than or equal to delta, is less than or equal to mu over delta. All right. Have you seen this before? How many of you have not seen Markov's inequality before? Okay, you have not seen it. No problem. How do we prove this? Does anybody remember? Let's start with a simple case. Let's assume that x is a continuous random variable. You can do the same thing for a discrete random variable and in more generality, but it at least gives the insight as to how you prove this. What is expectation of x? Sorry?
We expand that and then
Correct. So let's start with that. What is the expression for expectation of x? It is integral from minus infinity to infinity x times fx of x dx, right? Sorry.
minus infinity to sigma.
Let's do it step by step, right? So x is a non-negative random variable, right? So fx of x is 0 for x less than 0. So this is just equal to integral from 0 to infinity x times fx of x dx. Now, as you rightly pointed out, I'll just split this into two parts: integral from 0 to a x times f of x dx plus integral a to infinity x times f of x dx. All right, and this is crucial, that this integral from minus infinity to 0 is equal to 0, right? What can I say about the first term? What is sigma? I don't have sigma, right? It's at most a, but that's not what I want. All right. So this quantity is always non-negative. You agree? It's at least 0. So this quantity is greater than or equal to 0. So mu is greater than or equal to integral from a to infinity of x times f of x dx. All right, this is fine. Okay, that's good. Now mu is greater than or equal to, so this is integral from a to infinity of this particular quantity. In this entire integral, the x takes the value at least a, right? So this is greater than or equal to integral from a to infinity a times f of x dx, right? That's essentially all I need. I take a outside, I get integral from a to infinity f of x dx. But what is this particular quantity over here? It is the probability that x is greater than or equal to a, right? So this is equal to a times the probability that x is greater than or equal to a. So mu is greater than or equal to a times the probability that x is greater than or equal to a. Probability x is greater than or equal to a is less than or equal to mu divided by, right? Any questions so far? Okay, that's fairly simple. So this is a very simple inequality, but in itself it's not very powerful. It's restrictive because x has to be a non-negative real number, has to be non-negative, a random variable. And if you look at the right hand side, when is this inequality useful? For what values of a is this useful? Of course a has to be non-zero, but beyond that, this inequality is valid when a is non-zero, of course. It has to be greater than mu, right? Because if a is less than mu, then I get something greater than 1 on the right hand side. I know that the probability of any event is at most 1. So the right hand side is completely non-informative. So it gives me something non-trivial only when a is something which is greater than mu. Right, and it holds only for non-negative random variables. I want something more general. So although this in itself is not terribly useful, this is the starting point for essentially all other concentration inequalities that we will see. So the next better inequality that we'll derive is the Chebyshev inequality. So the inequality is the following. So if x is any random variable with mean equal to mu, which is finite, and variance equal to sigma square, which is also finite, then for all delta greater than 0, the probability that x minus mu, so the probability that the deviation of x from the mean is greater than or equal to delta, happens to be less than or equal to sigma square over delta square. Alright. Now before we prove this, let's just pause and look at this inequality in the first place. So we are of course interested in the probability that the random variable deviates from the mean by a certain amount. So suppose we have some kind of a PDF that looks like this, right? So let's say I have some kind of a distribution, need not be symmetric, but whatever. So the mean is something, maybe perhaps this is the mean, right? So we're interested in the probability that the deviation from the mean is at least delta. So this is delta, and this is also equal to delta. So the probability is simply equal to essentially you can think of this as the area under the curve in these regions, right? So that's what the probability is. Now if you fix a particular delta, it's kind of natural to expect that as the variance increases, that is as the PDF becomes fatter and fatter, the probability would become higher, right? That is the area under this particular region would increase, right? Area under the curve in this region would increase, and conversely, as sigma decreases, as the variance decreases, the density would become thinner and thinner. So the probability that, or the area under the curve in these regions would become smaller and smaller. Right. So if the variance decreases, then probably you have something like this. The PDF would become taller but thinner. Right. So the area under this particular curve in the region to the right of mu plus delta and to the left of mu minus delta, this would decrease. Right. So this is kind of a natural, this is what we would naturally expect to happen, and that's what the inequality is also telling us, right? So right now one thing to note is that the right hand side, or the bound that we get, is independent of the mean. It only depends on the variance. Okay, so how do we prove this particular statement? Square of?
Square that factor.
Okay, so let's take the random variable y to be equal to mod x minus mu squared, which is the same as x minus mu the whole square, right? What is expectation of y? Yeah, it's just expectation of x minus mu the whole square, which is just the variance itself. So the probability that mod x minus mu is greater than or equal to delta, because both the left hand side and the right hand side are non-negative, this probability is equal to the probability that x minus mu the whole square is greater than or equal to delta square. Alright, so if I didn't have this mod, then the probability that x minus mu is greater than or equal to delta is not equal to the probability that x minus mu the whole square is greater than or equal to delta square. I have to be more careful. But in this case it's non-negative, so this equality holds. So this is equal to the probability that y is greater than or equal to delta square. By Markov's inequality, this is less than or equal to expectation of y divided by delta square, which is just sigma square divided by delta square. All right, that's straightforward. Okay, so this is nice because now we have a more usable sort of tail bound. So essentially, any bound on a probability of this kind of a probability is called a tail bound, because in some sense you can think of this particular probability as the probability under what I call the right tail, and this is basically the left tail. So these are what I call tail probabilities, and now we have a bound on the tail probabilities. But for individual random variables, these are not terribly interesting on their own, because okay, let's say I take a Gaussian, maybe I can try to get an expression for this, but in general, of course, it's going to be bad. For example, even for the case for a univariate Gaussian, this bound turns out to be very, very weak. You can get a much better bound, but also, yeah, it's not terribly interesting. It becomes interesting when I have a function of n random variables. So let's go back to our original example of tossing coins, right? So you toss n coins. Maybe the bias or the probability of getting ahead is equal to p, which is between 0 and 1. And the goal is to find out what is the fraction of heads. What is the probability that the fraction of heads is close to p? We know that for large enough n, the fraction of heads should be close to p. But how close is it to p? So let me define the random variable xi to be 1 if you have a head. So it takes the value 1 with probability p, and it takes the value 0 with probability 1 minus p. Right? And x1 up to xn are independent and identically distributed. Right, which the fraction of the number of times I get ahead over n. So I toss n coins, I get k heads. I want to know what is k by n. So again, is anyone not familiar with the term independent and identically distributed random variables? Okay, that's good. So essentially this means that the joint distribution of x1 through xn is essentially equal to the product of the marginals. And all the marginals are the same. Right? And my goal is to analyze the following quantity Sn, which is the number of heads divided by n, which I can write as summation I equal to 1 to n xi whole divided by n. So what is the mean of Sn? Yes. Yeah. It's equal to P, so it's equal to expectation of x1 since they are independent and identically distributed. It's a Bernoulli random variable, so it's equal to P. And what about the variance? Sn minus P the whole square. So what is the variance of a sum of IID random variables? It's equal to the sum of the variances, right? But so expectation of I guess let me write it in the following way. This is expectation of 1 by n summation I equal to 1 to n xi minus p the whole square which is equal to expectation of, now let me take the 1 by n outside. What do I get? I get 1 by n square times the expectation of summation I equal to 1 xi minus n times p the whole square, which is just 1 by n square expectation of summation I equal to 1 to n xi minus p the whole square. So if I call this yi, xi minus p to be yi, what is the mean of yi? What is expectation yi? 0. What is expectation of yi square? Yeah.
P minus P square.
P minus q, so p into 1 minus p. So this is equal to p into 1 minus p, right? And these are all independent. So expectation of the summation of yi the whole square is equal to summation of expectation yi square. So this is simply equal to n times p into 1 minus p divided by n square, which is p into 1 minus p whole divided by n. All right. So what we finally have is that the probability that the fraction of times you get ahead, the fraction that you get ahead, the deviation of this from p is great. Sorry, let me do that the next step. So right now I have the variance of Sn. So using Chebyshev's inequality, the probability that the fraction of times I get ahead, the deviation of this from p, this is equal to, or this is less than or equal to p into 1 minus p whole divided by n. And what happens to this as n tends to infinity? This tends to 0, right? And that's exactly what we expect to happen, right? As the number of times you toss the coin increases, the this divided by delta square. It's sigma square divided by delta square, which is p into 1 minus p divided by n whole divided by delta square. So if you fix a particular delta, right? So if you fix the deviation, as you increase n, the probability that the deviation from p is more than delta vanishes. Right? And that corresponds to the experiment that we ran in the previous class. Right? You fix some particular interval, let's say 0.01 away from the mean. So if you fix that particular interval, as you keep increasing n, the histogram of the fraction of heads, it became taller and thinner. And at some point it was almost like just one particular spike. Right. And that's exactly what Chebyshev's inequality is telling us. Right. Any questions? Okay. So, well, Chebyshev's inequality is extremely good, but unfortunately, it's not the best inequality. We can get much tighter inequalities. In this case, what is the dependence on n? So, of course, this was the special case of Bernoulli random variables. But in general, if you take, let's say, we want to find what is the probability that Sn deviates from mu by an amount delta, where this Sn is the average. Xi is IID, but need not be Bernoulli. It could be any distribution. Okay. So no matter what you do, you'll always get the variance of xi, or maybe x1, divided by n delta square. It's easy to see why this is the case based on our previous example, right? So Chebyshev's inequality will give us a bound for which the probability that this deviation is greater than delta, it decays as 1 over n, right? The important point here is the dependence of the bound on n, on the number of samples that you have. So the best that Chebyshev can give us is a 1 over n dependence. And for many applications of interest, this is not enough. In fact, for many classes of random variables, the dependence on n is not actually linear, it's actually exponential. You can prove that this is in fact less than or equal to e to the minus some constant times n. But the constant depends on maybe the variance and other properties of the distribution. And that will be the goal of this particular course. Trying to derive not just any bound on the tail probability, but rather exponential tail bounds on the tail probability. That's what we want to aim for.
Instead of having the 1 by n, we need to go with the exponential.
Correct. Because for some applications, a 1 over n decay is not enough. In many cases, that's good, because it's not easy to derive exponential tail bounds in general. The advantage of Markov's inequality and Chebyshev inequality is that it holds true no matter what the distribution is. All right. So all you need is that the variance is finite and the mean is finite. All right. So this particular bound that I have written over here is independent of the distribution of x1. Whether x1 is Bernoulli or Gaussian or Laplace or gamma, doesn't matter. Whether it's non-negative or non-positive or both positive, negative, doesn't matter. This bound always holds. Right? So in that sense, it's a very useful tool. But because it is so general, it doesn't give you the best bound. It helps to specialize yourself to a certain class of distributions. All right, and that's what we will do. We'll restrict. So as we go along, we'll make restrictions. We'll first derive a very general bound, which is very powerful, but unfortunately not useful in itself, because it's very difficult to evaluate the bound in most cases. And then we'll try to specialize to classes of distributions, to specific functions. So for the first part of the course, at least for much of the course, we'll assume that the random variable of interest is always the average of IID random variables. All right, so Sn will be equal to, so we will always be interested in this particular quantity. Right, we'll thoroughly analyze this particular random variable, and then later we will go along and try to look at slightly more complicated functions of n IID random variables. Right, when right. Okay, so I'll maybe very quickly introduce to the next bound, and then we can stop there. So the bound using which we'll define other bounds is the Chernoff bound. And it says the following: if x is a random variable such that the moment generating function exists, then the probability that x minus mu is greater than or equal to delta, this is less than or equal to the moment generating function evaluated at t divided by e raised to t times mu plus delta. So this holds for all t greater than or equal to 0. All right. So essentially I have a free parameter on the right hand side, which is t, and for every t I get a bound. I'm sorry?
Is delta also?
Delta is of course positive. So this gives me a bound on the right tail, but I can also derive a bound on the left tail. The probability that x minus mu is less than or equal to minus delta is less than or equal to px of minus t whole divided by e to the t times delta minus mu. Again, this holds true for all t greater than or equal to 0. So this gives me not just one bound, but in fact a family of bounds, because for every t I get a bound. So in fact I can try to, since this holds true for all t, I can try to minimize the right hand side over all possible t and get the best possible bound. The proof is again straightforward. It's just an application of Markov's inequality. Right. So we have probability. Let me just look at the first quantity. X minus mu is greater than or equal to delta. This is equal to the probability that t times x minus mu is greater than or equal to t delta, because t is greater than or equal to 0. Right? In fact, let's assume that t is strictly greater than 0. This is equal to the probability that e to the t times x minus mu is greater than or equal to e to the t times delta, because the exponential is a monotonically increasing function. E to the t times x minus mu is a non-negative random variable, right? So if I just apply Markov, then I get that this is less than or equal to expectation of e to the t times x minus mu divided by e to the t times delta, which is nothing but expectation of e to the t times x times e to the minus t mu divided by e to the t times delta, which is just the moment generating function divided by e to the t times mu plus delta. Right? Nothing else. It's just the same thing. You just start with Markov's inequality. Whatever you have, you try to modify it so that you get a non-negative random variable and apply Markov's inequality. That's it. Alright. So this gives another bound, but now it's extremely complicated because it's in terms of the moment generating function. For certain nice random variables, you can evaluate the moment generating function, but now you have the problem of choosing t, which is for specific classes of distributions. You can find this. You can find the best possible bound. For example, for Bernoulli, Gaussian, and other such simple distributions, that's easy to do. But in many applications, you don't even know what the actual distribution is, but you only have certain properties of that particular distribution. In those cases, using the Chernoff bound is not easy. But we'll see that the Chernoff bound you can sort of look at special cases wherein just by knowing certain properties of the distribution, you can use the Chernoff bound and get a bound which in fact is sort of an exponential tail bound. Okay, so we'll see more of that in the next class. Any questions? Okay, so if not, let's stop here. So another quick announcement.